So, welcome to the new lecture again of the course Fundamentals and Application to Electric Ceramics. So, let us just briefly recap the last lecture. So, in the last lecture we completed our discussion on domains in ferroelectric materials, and we saw how the domains evolved during ferroelectric switching, going from zero polarization to very high saturation polarization, then reverting the switch field back to zero brings us back to the state of remnant polarization, where there is unequal volume fractions of up domain with respect to down domains, or vice versa, depending upon minus PR or plus PR, and then how you have to again apply a electric field, extra electric field, to force the system back to zero polarization state, which is the coercive field. So, domains are very important and their size is very important. So, factors which play important role are domain size, switching kinetics, etc., which are out of purview of this course, but these are very important factors, and domains are affected by, for example, things like grain boundaries, how domains switch is a function of grain size in the system. It is also a function of defects in the system, defects and impurities, and so on and so forth. Okay. So, this is a topic of basically this is a topic which frequently is faced by researchers working in the area, whose aim is to synthesize good ferroelectric materials. And then we looked at some common examples. And common examples, as we saw, were things like lead titanate, barium titanate. You can have PbZrO3, solid solution of PbZr and Ti, which is the most common ferroelectric, PbTiO3. Then we have BiFeO3, we have solid solution of BiFeO3 and PbTiO3, and so on and so forth. And of course, we have polymeric material, which is PVDF and its copolymers. Okay. So, there are quite a few examples of ferroelectric materials. Of course, PZT is the benchmark material because of its high piezoelectric coefficient, but other materials are also equally interesting as well as useful. So, let us just look at the phase diagram of PbZrTiO3. So, the phase diagram of PbZrTiO3 is something like this. So, let us say you start from PbZrTiO3 on this, ZrO3 on this side, and then we go to PbTiO3 on this side. So, obviously, the Tc is high on this side, Tc is lower on this side. So, if you plot a line between the Tc, it goes something like this. So, this is sort of a phase boundary. At lower values, it sort of has a phase boundary again. So, these are various regions which go in this material. Now, as it turns out, at higher temperatures the material is in cubic, that is in paraelectric form. At lower temperatures, PbTiO3 rich compositions have tetragonal structure, and this boundary which is here is called as morphotropic phase boundary, at which is a basically sharp boundary between tetragonal region and the adjoining region, which is rhombohedral region. This boundary separates the two, and basically this is a region in which these phases sort of, we can say, coexist. So, within the vicinity of this boundary, so within you can say the vicinity of this boundary, MPB, both tetragonal and rhombohedral phases coexist. And this coexistence two phases basically increases the number of polarization vectors you can have material, because in tetragonal you can have this vector or this vector, whereas in rhombohedral you can have vectors along 1 1 1 direction, right. So, you can have PR vector in this direction, this direction, this direction, this direction, this direction and this direction, as well as this and that. So, in this case you will have 1 1 1 PR vectors, and in this case you will have 0 0 1 as PR vector. So, when both of these coexist, number of polarization vectors are larger. As a result, it leads to easier switching and higher D33. So, this gives rise to higher D33, and this is at a composition of 47:53, nearly 47% PbZr TiO3 and 53% PbTiO3. Okay. So, PbZrO3 of 57, 47 and 53 of PbTi. Somewhere at the corner at low PbTiO3 concentrations, the material is antiferroelectric. So, pure PbZr TiO3 is antiferroelectric. So, antiferroelectric material we have not discussed, but basically it shows loop like this, something like this. So, it has some sort of hysteresis. So, this is 0 electric field, this is E, this is P. So, in the first and third quadrant it shows some sort of a hysteresis, but at 0 electric field it has 0 polarization, just like antiferromagnet. So, at 0 magnetic field antiferromagnet has 0 magnetization. Here also at 0 electric field you have 0 polarization, but when you mix it with PbTiO3 you achieve some interesting qualities. So, this is 490 degree centigrade, this is 230 degree centigrade or so. So, this would be approximately the mathematical sum of 2, approximately speaking. So, it is a fairly straight line, although it is a little bit non-linear, but approximately it just goes by the rule of mixtures. So, on the left you have antiferroelectric region, which is generally not very useful for most applications, but the useful compositions are these rhombohedral and tetragonal, and the most useful of them is this MPB composition of nearly 50-50, you can say, a 47-53. So, in the vicinity of MPB people make piezoelectrics which have D33 values exceeding 1000, or in fact even very high values have been reported. So, this is one material that is there as a ferroelectric, which is very useful, and similar MPBs are shown in you can say similar MPB effects are seen in systems like BiFeO3, PbTiO3, BiFeO3, BaTiO3 and so on and so forth. Quite a few systems show this MPB, and this MPB is quite exploited phenomena for exaggeration of properties in the vicinity of MPB. So, these are so this is sort of an example of a good ferroelectric material. Okay. Now, let us see, for example, what happens in case of barium titanate. Barium titanate is a very famous material. So, barium titanate, when you measure its dielectric constant, the dielectric constant of barium titanate as a function of temperature, it shows 3 sort of, you can say, kinks. Okay. So, the kinks are something like this. So, you start measuring the dielectric constant, it goes something like that, then it goes boom up, then again sort of shows behavior like this, then again, and then again it shows, and these 3 temperatures are, and this there is a hysteresis as well. So, when you take it back in the opposite direction, so this is in the forward direction, this is in the reverse direction, and again this is in the forward direction and this is in the reverse direction. So, how you make the measurement, it is like this, okay, something like that. Okay. So, there is a hysteresis in Tc, but this happens at about minus 90 degree centigrade, and this happens at about 5 degree centigrade, and this happens at about 120 degree centigrade, and the crystal structure goes from rhombohedral to orthorhombic two tetragonal, two cubic. So, this is the paraelectric state. This is the high temperature paraelectric state at above 120 degrees centigrade, but below 120 degrees centigrade it has two more transitions and they are from one ferroelectric state to another. So, this is also ferroelectric, this is also ferroelectric and this is also ferroelectric. It is just that dielectric constant changes. So, in the tetragonal state we achieve highest dielectric constant, whereas in orthorhombic and rhombohedral regions we observe lower dielectric constant. Of course, the temperature is also lower. So, polarization of the lattice is also lower. And as you can also plot dielectric constant. When you plot the dielectric constant, similarly you can also plot the lattice parameters. So, in this case you will observe two lattice parameters. In the orthorhombic case you will observe three lattice parameters A, B and C, whereas in case of rhombohedral you will observe only one lattice parameter. So, you can also plot across these temperatures. If you plot lattice parameters A, B and C as a function of temperatures, you will see this kind of changes. So, rhombohedral will show something like this, and then depending upon whether you heat or cool, so you will have basically three lattice parameters here. So, A, B, C, and then in this region you will have A and C, and then again you will have cubic somewhere here. So, this is the TC region. So, this is the TC region you will have. So, here you will have rhombohedral, you will have only one lattice parameter. Here you will have three of them, orthorhombic. So, you will have, let us say A, B and C, and then here you will have C and A. So, this is tetragonal, and then we have cubic only A. So, one can also measure lattice constants as a function of temperature using techniques like X-ray diffraction, and one can see this variation in reality in these materials. And the polarization vectors are also different. In cubic you have no polarization, here you have polarization along 0, 0, 1. Okay. In the other case you will have polarization parallel to 1, 1, 0 axis in the orthorhombic case. So, you will have, so when you say P 0, 0, 1, you will have two directions, right. You can have 0, 0, 1 or 0, 0 bar 1. In the 1, 1, 0 case you can have 12 directions, right. In case of P parallel to 1, 1, 1, you can have 8 directions. So, this is how the polar vectors will also change as you change the material. And generally in the tetragonal form, the way it happens is that in tetragonal form, when you convert this to tetragonal phase from cubic phase, so you will see the structure will show some sort of distortion. So, these are all oxygen atoms sitting at the center of phases. This is barium atom. So, this is barium, this is oxygen. In between we will have a tiny, so this is the center of the lattice. Your titanium atom will either be here or it will be here. So, this is, let us say center of the unit cell. The titanium will be shifted up or down, and the magnitude of displacement is about, if you draw the cross section, the displacement is of the order of about, you can say a few picometers. So, the displacement off center displacement is of the order of, let me see the number, it's about 11 picometer. 11 picometers. So, you can calculate the dipole moment. So, dipole moment will be q dot d. Q is 4 electrons, 4 into 1.6 into 10 to the minus 19, and d is 11 picometer. So, you can calculate the dipole moment. Accordingly, you can calculate the dipole moment per unit volume, which will give you the polarization. So, sort of you can get an estimate of polarization by just measuring the dipole moment in this fashion. So, this is about TiO3 and some examples of ferroelectric materials. Remember, all these ferroelectric materials are also piezoelectric and pyroelectric in nature. So, you will see that many piezoelectrics and pyroelectrics which are used in practice, they are actually ferroelectrics, okay. Just because materials like PbTiO3 and solid solution of PbTiO3 with PbZrO3, they have high D33 values in the vicinity of mpb. That is why they are used as piezoelectric materials as well as pyroelectric materials. So, now let us look at some of the applications of, okay. So, we first see how do you measure the ferroelectric polarization. Ferroelectric polarization is generally measured using So, ferroelectric polarization is generally measured using a circuit called as Sayre-Tower circuit, okay. So, what you have in this circuit is basically it's a very simple circuit, it is not a very difficult circuit. So, you have a circuit like this. Let me just draw this first and then explain it. So, what you have is you have an oscilloscope on which you read the polarization. So, you can have X and Y. So, this is basically you can say is a you need an oscilloscope. Nowadays, you can get rid of oscilloscope, you have electronic circuits and computers. So, you do not need that, it can just be connected to computers. You need a signal generator, so that you can provide a AC field. So, this is signal generator. So, which means you must have range of voltages and range of frequencies. Generally, the frequencies that we measure used for ferroelectrics are somewhere between 0.1 hertz to you can go up to few megahertz, okay, and the voltages will depend upon the thickness of the sample, but voltages may also vary from 0.1 volt to few kilovolts, okay. They may not be available on single unit. So, you may have a unit up to 200 volt. So, 0 to 200 volt plus you can have something which is up to 10 kV, okay. So, if you have a sample of let us say thickness 1 millimeter or let us say half a millimeter, 0.5 millimeter. So, 10 kV will give you a field. So, 10 kV divided by 0.05 centimeter. So, this is in kV per centimeter. So, this will give you very large field, okay. So, you can see you can do the calculations yourself, and we'll have fields in the order of megavolts per centimeter. So, which is large enough field. So, switch any ferroelectric. So, if you have a 10 kilovolt power supply with frequencies varying from 0.1 to few megahertz, and generally we make the measurements at about 100 hertz to 10,000 hertz, okay. This is a general range for making measurements, but it depends upon the material and just application. So, one should be able to measure most ferroelectrics if you have this system. Now, what happens in this circuit is basically you apply this signal to a ferroelectric. So, this is a ferroelectric under test. This ferroelectric is connected in series to in parallel to your reference capacitor. You must always have a reference, because you are measuring the charge or polarization. As a result, you have to have a reference, otherwise you need something to calibrate the system, and this reference is earthed. So, basically you can see the circuit is very simple. You have a reference capacitor and you have a ferroelectric which you measure in comparison to this reference. You have a signal generator which is to generate the kind of voltages that you would like to apply on the sample. Then you have an oscilloscope. oscilloscope is nowadays replaced by computer and software, so it's much more easier to make the measurements. The kind of measurements you may make on ferroelectrics are you can make DC measurements. So DC measurement is just for measuring the DC conductivity, okay, just the ohmic losses. But most of the measurements that you make are AC measurements, that is time dependent measurements. So time dependent measurements could be your polarization hysteresis loop measurement, okay. You can make dielectric measurements, so this is DC conductivity is basically, you can say it's a IV measurement, okay. So you can measure ampere, so you can measure either I or J. J is the current density as a function of electric field. So current versus voltage or current density versus electric field, make sure that you know whether it's current or current density. If you want to have current density, then you need to have the measurement of electrode area accurately. So generally how you make this measurement is, you have this capacitor sample, on that we make these electrodes. Electrodes are typically metallic electrodes made of silver or gold or platinum. You have to choose a metal which does not inject charges. You have to have a non-injecting and you should have a ohmic contact. You should not have a Schottky contact. So generally the choice of metal is silver or gold or platinum. You must try and make an electrode which makes a good contact. If you don't have a good contact, you are going to have defects at the interface, and this is going to lead to very poor measurements. So generally we prefer the contacts which are evaporated contacts, and after evaporation or or printing, you will have to anneal them to make a better contact. Annealing can be done at a little lower temperature, but thermal treatment may often be necessary. So you have a ferroelectric which is sandwiched between these two electrodes. In order to calculate the current density or the charge density, you must know the size of this electrode. Size of this electrode, especially basically the diameter of the electrode, is very important for the calculation of any quantity in terms of per unit area. So polarization will be microcoulomb per centimeter square. You need to know the electrode, and electric field, which is kV per centimeter, and this requires you to note the thickness of sample very carefully. So what you require is electrode size and thickness of sample. So DC conductivity measurement will tell you whether your sample is conducting or not. If it is conducting, it is probably not worth making any other measurement. You just have to make a better sample, because ferroelectrics are supposed to be insulating. So general guideline is, if your current density is less than, if J is less than 10 to the power minus 6 amps per centimeter square, then it's a good material. But if it is more than 10 to the power minus 6 amps per centimeter square, then it's a pretty bad material. It's a leaky material, as we say it. So this is sort of a general value. I mean, it varies from material to material, but sort of a range. You make a ferroelectric hysteresis loop. Ferroelectric hysteresis loop, in the literature you will see people report hysteresis loops of various kinds. You will see people measuring this kind of hysteresis loop, people measuring hysteresis loop of this kind, people measuring hysteresis loop of this kind. This is a reasonably good hysteresis loop. You must have a saturation in a nonlinear region. These ferroelectrics are bad hysteresis loops, and most likely these materials are not ferroelectric. They are leaky dielectrics basically. They have a lot of electrical leakage in them. There is a nice paper by Professor Jim Scott on Journal of Physics C, which says that ferroelectric goes banana. Go bananas. You can search it, this paper. It shows that even if you make a measurement on a banana, you will get a loop. So it is important to differentiate between a good loop, a proper ferroelectric loop, and a and a non-ferroelectric loop. So, any measurement which shows rounding of hysteresis loop tip, wherever you have lot of rounding at the tip or a very bloated kind of ferroelectric loop, that is probably not a ferroelectric. It may be ferroelectric at lower temperatures, but certainly there is a lot of leakage in the material which does not give you the intrinsic ferroelectric character. Intrinsic ferroelectric character must always result in this kind of loop. You must have a saturation, and this is what we are striving for. This is what we want. We do not want the red ones and these black ones. These are not good loops. And so, as a result, there is a need to make, if you get these kind of loops, there is a necessity of making temperature dependent measurements, because at lower temperatures the ohmic contributions will become lower. As a result, you might get saturation at lower temperature. So, temperature dependent measurements are the key. Then also dielectric constants. For a good ferroelectric, the dielectric constant you should measure should show a behavior like this. Okay. Low frequency will have some interfacial polarization, but in the middle frequency then you should have a pretty flat region. So, this is a good dielectric measurement where you do not have where between the relaxation regions dielectric constant is frequency sort of independent. Or sort of a poor quality of material would be like this, something like this. So, your dielectric constant varies as a function of frequency. Now, this poses a lot of challenges in terms of measuring the true dielectric constant, which means because your dielectric constant is varying as a function of frequency, which means there are other factors which are contributing to dielectric constant, and those other factors could be defects, generally defects arising from grain boundaries or oxygen vacancies or point defects. They contribute to dielectric constant themselves, polarization. As a result, you have frequency dependence, and that is where you need to do what we call as you need to do impedance analysis, impedance spectroscopy, to ensure the distinction between resistive and capacitive components, the ohmic component, non-ohmic components, and you need to model the ferroelectrics on the basis dielectrics and ferroelectrics appropriately, so that you can get the real capacitance, and from that you can estimate what is the real dielectric constant. You cannot calculate the dielectric constant from this measurement. You have to do the impedance spectroscopy to separate out the resistive and capacitive contributions to calculate the real dielectric constant. If anybody does that in the literature, it is purely wrong measurement. It is not a right way to report the data. And then you can also do AC leakage measurements. So, frequency dependent IV measurements or JE measurements, and then also people do I versus T measurements or P versus T measurements, that is time dependent stability of polarization and current. These are also very important measurements for various applications, where for a ferroelectric you should not see a decay in the polarization as a function of time. If you have a memory, for example, the memory should not lose its charge as a function of time, right. So, that is where we make these time dependent measurements. And finally, if you are making memory, then what we make is a fatigue measurements, where you switch the ferroelectric for more than, so if you apply pulse once, it is one cycle, but if you do it for millions and billions of cycles, it becomes fatigue measurements, and that is what you should do for ferroelectrics, piezoelectrics or ferroelectrics which are going to be used for multiple times in various applications. So, these are the various, they are just few measurements, the basic measurements. You need to ensure that your electrode is of correct type, generally a material with high work function, silver, gold or platinum. Better if you evaporate it, but even if you put it in terms of liquid, you must dry it quickly, make sure that it does not percolate through the sample, and make sure that you measure its dimensions correctly. And that is why use of masks is very important, and make sure sample thickness is uniform, otherwise electric fields are not going to be uniform, as well as your sample dimensions are noted correctly. You can make DC measurements of leakage, you can make AC measurements of leakage, you can make ferroelectric measurement, dielectric measurements, as well as impedance measurements, time as well as temperature dependent, and make sure when you are doing a ferroelectric work, your hysteresis loop should be like this, not like the one which are shown not like the ones which are shown in black and red. They are not good ferroelectrics. Okay, so we will stop here today, and in the next class we will look at the applications of ferroelectrics, piezoelectrics and pyroelectrics before we finish this course. Thank you.